part of our discussion on regression, we're going to revisit the correlations. Now remember, correlations represent a numerical value that describe the relationship between two variables, and it helps us understand how one variable moves in relationship to another variable. One of the most important notions in analytics is the variance. And we had looked in previous models how to use the variance for our confidence intervals as well as for our comparison of means and our t-tests and z-tests. Now remember that the variance is the sum of the square of the distance of each observation in the data from its mean, divided by the number of observations. So it's basically the average distance. We take each point and we subtract from it its mean. So some will be above the mean, some will be below the mean. And we square it so that we can get rid of negative numbers. Consider if we had a 4 and our mean was 2, we would have a positive 2. But if we had a 0 and the mean was 2, it would be a negative 2. And so what happens is that the distance would be 2. And this is one of the reasons why we square it. Also consider if we had a 10 and our mean was 2, then the distance would be 8. By squaring that, you would have 64. So you're magnifying the effect of these observations that are further away from the mean. The covariance is a way to describe how two variables covary with each other or move with each other. And the formula on the right is similar to the variance formula. If you see, it's got the sum, but instead of xi minus x bar squared, what we're doing is we're taking the distance between the individual x observation and its mean and multiplying it by the individual y observation and its mean. And then we're dividing by n. So the problem with covariance, as we had said before, is that it is difficult to interpret unless the units of both variables are the same. And so this is why that we have a concept of a correlation. Now you may recall that from previous modules we had calculated a z-score, and a z-score is a way to standardize values so that they can be compared. Remember, from our standardized normal distribution with a mean of 0 and a standard deviation of 1, the numbers would go from negative infinity to positive infinity, but each z-score represented the number of standard deviations away from the particular mean. So whether you had one variable that was in miles and another variable that was in, say, revenue, you could actually standardize and get a z-score to figure out how far away it was from its mean, and then you can compare them. The importance here is that the correlation is the standardized covariance. That basically means that we're dividing by the standard deviation. And in this case, we're dividing by the standard deviation of x times the standard deviation of y. So we're taking the covariance and dividing it by the product of the standard deviation of x and the standard deviation of y. Our correlation value is represented by either an r, lowercase xy, or sometimes we'll see it with the Greek letter rho. Correlation value will be a number between -1 and 1. And in previous modules, we had shown that numbers that were close to 0, either on the negative side or positive side, from around -0.2 to positive 0.2, represented no correlation. And the further away it was from 0 would indicate how the strength of the correlation in either the negative or the positive direction. So calculating the correlation in Excel is much easier than trying to use the formula to the right. We'll just use the Correl function. So here's a sample of 2 columns of data, and all we're going to do is apply the Correl function, C-O-R-R-E-L, with column A and column B data to give us a correlation of 0.98. So this is a very strong positive correlation.